Can you hear me? Is it okay like that? Fine. So, uh, in the next 15 minutes, I will give you a quick overview about the paper titled Malicious Internet Entity Detection using Local Graph Inference, which we wrote with Pevňák and Vašek Šmídl, and we submitted and got accepted in Transaction on Information Forensics journal. So, what was the problem? We have a computer network or internet network which can be viewed and represented as a graph. This graph is heterogeneous, meaning that there are nodes of several types. In this specific example, we have binaries in purple, domains in red, some URL paths in green, and emails in orange, and IP addresses in gray. And we have this internet network. We also know that some entities, some actors in this network are malicious, which are these entities we will also call tips, and they are usually as in a kind of blacklist or denial list of these entities. So, for example, here in this specific example, we have two domains which have name that consists of repeated sequences of characters, and this is quite a common tactic to mislead users with smaller screens and make them click this or make them not notice that they are on the wrong domain. So either of these two domains could, for example, be in our denial list. What can we do with that and with the network? So we can extend this denial list somehow. So for example, we can see from the network that these two domains somehow interacted with a common binary here, the big binary in purple. So what these edges in this network can mean? They can mean pretty much everything, but they are, in our case, they were defined as the simplest interactions that we can observe in the internet. So when we have an edge between a domain and IP address, that can mean IP address resolution. When we have an edge between a binary and a domain, that can mean that the binary communicated with this domain, meaning that it initiated one internet communication without any details. So our goal is, given this internet network and the denial list, we want to extend this denial list to, in the future, detect some threats in the network. So historically, there were two approaches to this. The first one is called feature-based, and this is what machine learning was about in its infancy. So we forget that there is a graph, and we represent each entity, be it URL or domain, with some kind of a feature vector, which is of fixed length. And once we do that, we can apply any off-the-shelf method, support vector machines, neural networks, decision trees, anything that can handle this type of data. And these approaches worked quite well. There's one very relevant work in this area. The problem is, and their biggest drawback is, that they don't use the graph at all. They don't use unless it is somehow encoded in the features. They do not use the graph at all. On the other side of the spectrum is something which we in the paper called graph-based approaches, and these, on the other hand, work with the graph as it is. So one very, again, prominent algorithm in this area is something called probabilistic threat propagation, which is inspired by graphical probabilistic models. And what this algorithm does is that it propagates the threat from the entities that we have in our denial list, it propagates the threat across the network through a concept called messages. So these messages are some quantities computed from these vertices in the network, and by propagating and sending these messages throughout the network, we can propagate the threat through the network. So this is depicted here in this picture. The trouble here is that once we have to deal with larger data, which in case of internet is really the case, these graph-based approaches do not scale well. So specifically this PTP algorithm, which was deployed in practice, needed hundreds of terabytes of RAM in order to compute something like that. And another consequence of this is that we can't really make the computation of these messages, let's say, complex. It's in PTP, the message as a quantity is defined in a very simplistic way. They do not use any learned model, for example, to express these messages as an arbitrary function. So, in the paper, we advocate third approach, or third line of thinking, which we call neighborhood-based approach, and it bridges the gap between the two worlds, and at the same time can nicely interpolate between each other. And what we do in neighborhood-based approach is that we select one specific vertex, which we call central vertex. In this case, it's this V, and we are now interested only in predicting, in providing a prediction for this vertex. So first step is that we select or we crop from the graph some kind of a neighborhood, small local neighborhood. In this case, I have shown a neighborhood with vertices that are one step away from the vertex, but could be larger. And we take this neighborhood, we forget everything else, and we work only with this neighborhood and provide the prediction based on the neighborhood. So basically, this is in machine learning jargon, this is our sample, and what we can do is that we can sample more. We can sample more of these vertices. We can perform some kind of stratified sampling. Suddenly, a lot of probabilistic techniques open for use. So this is one nice advantage of this approach. One important thing to note is that this stands on the obvious assumption that we can predict the threat of vertex in the graph, or basically its class, only on this small local neighborhood, which is a property that holds for the graphs that we dealt with in the work, basically internet graphs or graphs representing any kind of infected computer network. And also, you may have thought that there is a very prominent and huge class of models called graph neural networks that basically is more or less neighborhood-based approach. Why couldn't we use that? So the problem here is that the data that we deal with in this problem is very large. So we are talking tens of millions of nodes and nearly billion edges. So if we basically cannot apply graph neural networks with the complexity that they bring to this problem. So in these three graphs, depending on the T here denotes the size of the neighborhood or the steps that we take before stopping. And as you can see, both axes are in logarithmic scale. As you can see, GNNs, which are the topmost two curves, the purple one is for gradient computation and the red one is for forward pass. They do not scale at all. But our proposed method does. So this is why GNNs are not applicable here, basically. So what does our method different from GNNs? So there are two main concepts that I will talk about. Rest is beyond the scope of this lecture, but the first one is streamlined neighborhood subgraph, and the other one is the use of proper or convenient architecture to process this subgraph. So in order to construct streamlined neighborhood subgraph, we start again. This is a graph. This one is almost planar, but in reality, the situation is much more. As I told you, there's billions of edges, so the graphs we dealt with are nowhere near planar. But this is just for the demonstration purpose. We have again some central vertex that we are interested in, and what we first do is that we get rid of some edges that are not that important for the prediction. So in this, as you can see, this is a graph of shortest paths from V to any other vertex in the graph. So if any edge is not a part of shortest path to V from any vertex, it is discarded. We don't consider that. And this again comes from the observation that in this domain network graphs, the threat is distributed somehow very locally and in communities with sharp boundaries. So we can do that, and once we do that, we have we are left with a subgraph that also, if we orient it towards the central vertex, is directed a cyclic graph. So this is kind of a pre-processing step, and once we are done with that, we apply let's say special neural net architecture which can deal with tree and deck directed acyclic graphs data, something which we develop with Tomáš and is called HMLNet. So this HMLNet architecture can take us from here on the left. We have these types of entities in the network. This is split into several bipartite graphs based on the type of the node, and HMLNet architecture can take us from these graphs that we pre-processed with streamlining the neighborhood. It can take us to the prediction, taking into account the the threat of the nodes in the graph and also the topology of the graph. So very quickly, HMLNet architecture is just a hierarchy of trainable embeddings. So very hand-wavy, what we do is that we construct an embedding for each vertex in the subgraph, and we aggregate these embeddings together, and finally we are left with one embedding for the central vertex, and we throw a couple of layers on top of that to decide the class. So this is quite similar still to GNNs, but there is a big difference in complexity. And let me get to the results. So we compared to the PTP algorithm, the graph-based one that I talked about. The PTP algorithm works on the whole graph at once, and we cooperated with Cisco on that, so we got data from them, and we also used their implementation that they actually use in production for the PTP. And there's also one important distinction besides the fact that our method is trainable. So the messages that are passed in the graph inference are much more expressive. Our algorithm also can take multiple entities in the network. So at the beginning, I showed you a network with 5 types of entities. PTP can only deal with 2 of them. So these results are when we only employ 2 of these types of entities. As you can see, our method in red here is better, especially in region of recall 15 to 40%, say. But the even in my opinion more impressive results are when we incorporate more data. So when we take the same entities that we are interested in, but employ more data in, like, basically add more vertices in the graph, encoding interactions of these entities with each other, we can get to much better efficacy of the model. So here we get, like, depending on the metric, obviously 3 or 4 times better model. And as I said, this is on real world data, so we consider this quite a success. And this is it. So here's the reference. The paper has much more details. I couldn't cover everything here, but if there's any question, please ask.
If you have any questions, I'll just give you the microphone. So we have it on the recording as well. So raise your hand if you have any questions.
I have actually 2 questions. One is the assumptions that you, from the network, you know, like there's a training network, you know where the malicious vertices are, so that you can train and then you apply it and validate that. And the other one is your framework. I recall that you sometimes use the JSON, like hierarchical JSON, and learn on that. Is that the same idea? So you transform the shortest path reduced network to a JSON and learn that? Is that how I can think
Yes.
about it?
So the first question was about basically ground truth. So how it works in practice, or at least in Cisco, is that they have a huge list of malicious entities, and they know that these entities are malicious, and then there's the rest. So this is an instance of positive unlabeled problem, which we dealt with by basically stratifying the denial list, splitting it into training and testing set, and even though it's not true, there may be some threads that are uncovered that are not in the denial list. This stands on the assumption that there is not many. So we used this denial list as a ground truth, and also as an input to the algorithm. And the second question was about JSON. Yes. So one of the most used application of HTMLnet is on JSONs. Yes, and indeed, yes, it is true to encode the streamlined neighborhood as a JSON. So in JSON nomenclature, we have arrays. So you can encode basically the neighborhood of any vertex into this array, and you can build JSON from that, and after that apply HTMLnet, but we didn't do it because this like from the implementation point of view is wasteful. So it's much more faster to encode it directly, so to say.
So in your method, how do you select the central vertex, and how does the selection influence the performance?
So okay, let me go back. the assumption is that you select a vertex that you are interested in. So when we train, when the vertex is in the denial list, we don't predict it because it doesn't make sense, right? We know that it is malicious. So during training, we do not select vertices from the denial list, and we basically train on everything else. And so we have a positive class, the class that we consider negative, which is unknown in fact, and we train on that. And again, depending on how you want to calibrate your model, say, you can sample these vertices with different probabilities. Our method treats the input graph as a kind of database where you can from which you can take your samples in form of the central vertex and its neighborhood, and you can train on that. So say you want to sample a mini batch, which is done when training neural net. You sample 200 central vertices with some proportion of them being positive, some proportion of them being negative, and you train on that. This is different from the graph-based approaches, which always consider the graph as a whole. And during testing, it again depends on what you're interested in. So again, this approach has one big advantage in comparison to PTP, for example, is that you can predict only for a small amount of vertices in the graph. You don't have to run the whole procedure over the whole graph, huge graph, even if you are not interested. Even if you are interested in only a couple of vertices. And the last advantage I can think of is that when you have infinite graphs or streaming graphs, you can also apply this kind of sampling of central vertices. Yeah, but again, if you have a graph and you want to predict everything in it, you just take one by one and run the prediction in a for loop.
So TIFFs is a security journal, right? So is the contribution mainly to the security field, or is there some like machine learning contribution? And if you can sum up the machine learning one, and whether it has been published somewhere else as well, or whether you plan to somehow communicate the machine learning contribution to the machine learning community as well?
So yes, it was submitted to the cybersec journal, mainly because this type of data is quite unique, I would say, even though very very relevant in the domain. We tried searching for similar data in terms of scale, but there are not many, and the whole machine learning community, like core machine learning, really deals with GNNs and the data that they can handle. So like because of this fact, and also because of the fact that there is one technical detail that you need, and detail that I completely skipped here because of the time, but the fact that you can consume the input directly in the form of interactions or several bipartite graphs, we opted for a cybersec journal. Obviously, if we wanted to submit to some core machine learning conference or journal, we would need to delve much more into the difference between GNNs, the fundamental difference, because in some cases the computation is equivalent, in some cases it is not, the cases that I showed. And given the application, we just decided to submit there. About the other question, currently we have no plans to like continue with this application to network graphs, mainly because we are not in Cisco anymore, neither me nor Pevňák. So So yeah, that's it.